Today's lesson is section 7.2 from your textbook. We are looking at the sampling distribution of p hat, and in order to address this properly, you need to recall some stuff from the previous chapter. In chapter 6, we learned that the mean and standard deviation of a binomial random variable r, and those formulas are as they appeared in chapter 6. Since p hat is x over n, which equals 1 over n times x, we are just multiplying the random variable x by constant 1 over n to get the random variable p hat. Therefore, the mean of the sampling distribution of p hat is just p. Okay, the p hat, or the sample proportion, is an unbiased estimator. That should be for p. Recall what that means. A statistic used to estimate a parameter is an unbiased estimator if the mean of the sampling distribution is equal to the true value of the parameter being estimated. All right, the bridge from here to here, this stuff in the middle isn't particularly important in terms of what you need to know for a quiz or test. The important thing is the concept of the mean of the sampling distribution of p hat being p is a direct byproduct of what we learned in chapter 6. Okay, as far as the standard deviation goes, again, this bridge of stuff in the middle isn't overly important for what we accomplish in this particular class. The important thing is to realize that the standard deviation of the sampling distribution of p hat is a direct byproduct of what we learned in chapter 6. It's something that's going to be pretty important to us for the remainder of the course. As the sample size increases, the spread decreases. Okay, n represents the size of your sample. As the bottom of a fraction gets bigger, the value of the entire fraction gets smaller. So for a simple example, 1 over 10 versus 1 over 100 versus 1 over 1,000, the bigger the bottom of the fraction, the smaller the fraction itself. That smaller spread is an advantage to much of what we're going to be doing for the remainder of the course. All right, more details about the sampling distribution of p hat. Choose a simple random sample of size n from a population of size big N. So little n represents sample size, big N represents population size, with proportion p of successes. So p, remember, is a population proportion. P hat is going to be the sample proportion. Okay, so the mean of the sampling distribution, and this is the symbol, mean of p hat like that means the mean of the sampling distribution is equal to the population proportion. The standard deviation of the sampling distribution of p hat is this guy right here. P is population proportion, N is sample size. Okay, this is a valid formula as long as the 10% condition is satisfied, meaning we're not allowed to sample more than 10% of the population. Okay, as n increases, meaning as the sample size increases, the sampling distribution becomes approximately normal. Before you perform normal calculations, check that the normal condition is satisfied. So this is the same condition we checked in chapter 6. If our successes and failures are both at least 10, then we are going to be able to use a normal approximation. Okay, word of caution, and we've been here before with this same word of caution. When describing the shape of a sampling distribution, make sure you say approximately normal. Nothing in statistics is perfectly normal. Omitting an approximation description will cost you AP rubric points. All right, so here's a visual of what's going on here. You take a simple random sample of size n, you get your sample proportion, you plot it. Second simple random sample, same size, get a second proportion, plot it. Third simple random sample, size n, get the sample proportion, plot it. So if you plot every possible sample of size n, or the sample proportion of every possible sample of size n, you're going to get an approximately normal distribution. The mean of that distribution is going to equal population proportion, and that's going to be your standard deviation. All right. This is a chapter that's going to bridge our probability world to our inferential statistics world. It is important to realize that this chapter is a theoretical bridge between probability and the last part of the course. We do not actually take samples over and over again. Okay, that would be very impractical in terms of cost and money. But we consider what would happen if we did this in this chapter so we can draw the correct conclusion about one sample in the rest of the book. So it turns out that if you were to be able to take repeated samples over and over and over again, the results of that were extremely predictable by specific math rules. So we use those rules in order to accomplish what we're going to be accomplishing for the rest of the book. This is a theoretical bridge that addresses that what if we did, but typically very seldom do we ever do that. All right, so what are some typical types of questions you're responsible to be able to answer for this particular chapter? So here's our scenario for the first set of questions. About 75% of young adult internet users, 18 to 29, watch videos online. Suppose that a sample survey contacts a simple random sample of 1,000 young adult internet users and calculates the proportion in this sample who watch online videos. What is the mean of the sampling distribution of p-hat? So, reminder of what they're talking about here. If we were to take repeated samples of size 1,000 over and over and over and over again, for each one of those samples, calculate a p-hat, plot all those values, what would be the mean of that resulting distribution? The mean of the sampling distribution of p-hat equals population proportion, which according to this problem is 0.75. Okay, find the standard deviation of the sampling distribution of p-hat. Okay, we have a formula for this. That formula is only valid if the 10% condition is met. It's safe to assume that there are more than 10,000 young adult internet users, so the 10% condition has been met. If you are asked to verify this condition, always make sure you do so in the context of the problem. You can't make a generic statement like we didn't sample more than 10% of the population. You have to use specific numbers and talk about what the population is. So, the only number we need is that 0.75, plug it into the formula, and that gives us our standard deviation of the sampling distribution of p-hat for this problem. Okay, this is the same prompt as the previous slide. Now the third question is the sampling distribution of p-hat approximately normal? It's going to be approximately normal as long as we get that large counts condition being met. So NP has to be at least 10, and 1 minus P has to be at least 10. I'm not sure if we've addressed this or not, but some websites, some textbooks use NQ instead of N1 minus P. 1 minus P is the probability of failure. To make it a little bit cleaner, some books use the NQ as the notation for that. So N is your sample size, that's 1,000. Probability of success, probability of failure, they're both at least 10. Again, if you're asked to check this, you have to make sure you do so in context. Context for this question means you actually show the numbers. That the 750 and the 250, where did they come from, making a specific statement that they're at least 10. Okay, if the sample size were 9,000 rather than 1,000, how would this change the sampling distribution of p-hat? Well, the mean doesn't change with sample size. What does change is the spread. So instead of having, let's refer back to that previous slide. Instead of having an n value of 1,000, now we have an n value of 9,000. As the bottom of the fraction gets bigger, the overall value of the fraction gets smaller. So it would be a 0.0046 versus a 0.0137. And it turns out it's smaller by a factor of 3. We have that square root relationship going on. So increasing from 1,000 to 9,000 is times 9, but since it's underneath the square root, the net result is a factor of 3. So if we increased it from 1,000 to say 25,000, that would be times 25, that would be a factor of 5. Okay, another set of examples to illustrate these ideas. The Gallup poll asked a random sample of 1,785 adults whether they attended church during the past week. Let P hat be the proportion of people in the sample who attended church. A newspaper report claims that 40% of all U.S. adults went to church last week. Suppose this claim is true. Okay, what is the mean of the sampling distribution of P hat Y? Okay, the mean of the sampling distribution of P hat is equal to the population proportion. So in this case, mean of the sampling distribution equals P, which is 0.4. Okay, find the standard deviation of the sampling distribution of P hat. Check to see if the 10% condition is met. So the standard deviation of the sampling distribution, here they use the PQ instead of the 1 minus P for that one. Okay, this formula is valid as long as we're not sampling more than 10% of the population. And the 10% condition is met because the sample size of 1,785 is less than 10% of the population of adults. So again, if you're asked to make this check, it has to be in context. Everything we do pre-response is in context. Context would mean specific numbers. What is the population? So plug in the numbers, that gives us the standard deviation. Okay, is the sampling distribution of P hat approximately normal? Check to see if the large counts condition is met. So if NP and NQ, or again, you could do N1 minus P, as long as those are both at least 10, then the normal condition is met. Okay, in context, you have to state the actual numbers. If they weren't given in the problem, you need to show where they came from, and you have to make the specific comparison to the number 10. Okay, this is the same prompt up top about the people going to church. Okay, question number D, or letter D. Of the poll respondents, 44% said they did attend church today. We'll start that over. Of the poll respondents, 44% said they did attend church last week. Find the probability of obtaining a sample of 1,785 adults in which 44% or more say they attended church last week if the newspaper reporter's claim is true. Does this poll give convincing evidence against the claim? Explain. All right, so we know the mean of the sampling distribution is 0.4. We know the standard deviation of the sampling distribution is 0.0116. We verified that we can use an approximately normal distribution to model this. So normal CDF is fair game. So what's the probability of getting at least 44% when the mean is 40 and the standard deviation is this? So we usually use 10 to the 99th. Any arbitrarily large number will get the job done. 1,000 is large enough. I would say it's safer to go with this, but every once in a while you see a number not quite as extreme. Okay, speaking of at least extreme, reminding you of something that's been true for quite a while in the class. Very often we're not interested in that exactly 44. Results at least as extreme as 44. In this case, 44% or more. So probability is pretty low. 0.0003, so 3/100ths of 1%. There is a 0.003 probability of obtaining a sample in which 44% or more said they attend church last week. Because this is a small probability, there's convincing evidence against the claim. It isn't plausible to get a sample proportion this large by chance alone. So something's not correct here. Either that number is incorrect, or it's very possible a plausible explanation for this could be if you are being asked in person, if you've attended church, if you feel due to your moral upbringing that you should be attending church, perhaps you lied about going. A little response bias, depending on how this question was asked or posed. Just something else to critique in terms of this particular scenario. Same scenario about asking people if they go to church. Next question. What sample size would be required to reduce the standard deviation of your sampling distribution by 1/3 of the value you found in Part B? Justify your answer. So as a reminder, this is what we found in Part B. We want that to be 1/3 the size. So if we want that to be 1/3 the size, what we're going to have to do is increase that by a factor of 9, because remember that's underneath the square root. So we'd have to we'd have to survey 9 times that many people, or 9 times 1,785. So we'd have to survey over 16,000 adults. Now, one of the topics that we're going to be talking about for the rest of, in various places for the rest of the course, has to do with sample size. Well, how many people should you sample in order to obtain certain results here? And we have to balance this with cost and time. For example, how much more money, how much more time does it take to survey 16,000 people versus a little less than 2,000 people? Is that extra precision that we get worth that much more cost and time? So that's going to be something we're going to examine in a little bit more detail as we move through the course. All right, next setting here. According to Summit Entertainment, 80% of the audience for the opening weekend of the movie Twilight New Moon was female. If a random sample of 100 members of the audience were sampled, what is the probability the sample proportion of females would be greater than 0.85? All right, so in order to solve this problem, we have to go through some checks. One thing is we have to make sure that we're not sampling more than 10% of the total population. It's safe to assume that 100 is less than 10% of the total population who saw the movie in the opening weekend. Okay, so what this allows us to do is use a normal curve. What that allows us to do is to use this formula, and then the second one is what allows us to use the normal curve. Our NP and our NQ both at least 10, and again, you want to show what those actual NP, NQ numbers are, where they came from, and compare them specifically to 10. So we can use the normal curve, which means normal CDF is fair game. There's a little bit better than a 10% chance, about 10.5% chance of this occurring. Meaning in the sample of 100, we get a proportion of females to be greater than 0.85. Another example very similar to the one we just did. In the 2008 U.S. presidential election, 53% of the voters voted for Barack Obama. If a simple random sample of 75 voters were polled, would it be unusual if less than 40% of them voted for Obama? Okay, well, right away, when you see something like, is it unusual? Should you be surprised? Is it an unusual event? Blah, blah, blah. You're looking for that 5%. That's our default cutoff. If an event, the probability of an event occurring is less than 5%, you consider it to be unusual. So, getting to that particular probability number, we need to do our checks for this type of problem. We want to make sure that 75 is less than 10% of all voters in that election, or 10% of the total population. We got to make sure our NP and our N1 minus P are both at least 10. As long as those conditions get met, we can proceed like we did before. The 10% is what allows us to use the normal curve. No, 10% rather is what allows us to use, I said it backwards again, I apologize. The 10% is what allows us to use this formula. This is what allows us to use the normal curve. So we get only about 1.2% chance of that occurring. So with less than a 2% chance, you can classify it as unusual that less than 40% of the population voted for Obama. All right, there's not a whole lot in this class that requires you to be, apologize, to memorize formulas. Most of the key formulas in the class are provided for you. This is a snippet from The current formula sheet that you'll be given when you take the AP exam, to the best of my knowledge, is going to be the same formula sheet that was used last year. So in terms of where this stuff is located, if you're doing a p-hat from one population, the mean of the sampling distribution is equal to population proportion, and this gives you the standard deviation of that. This is something we're going to get to a little bit later in the course. We're also going to be doing the same problem, or extremely similar problem, with two populations instead of one population. We didn't get to that yet. And then the upcoming lesson in the next day or two is going to be the same idea, or the same basic ideas, except instead of doing it for proportions, we're going to do it for means. So I believe it's the next section in the book that we're going to address this part of the formula sheet. As far as the quizzes and tests you're taking here, well, if you're taking it home in a virtual environment, obviously it's open book, open note. You don't have to memorize formulas. If it's an assessment that's going to be taken in class that addresses this material, you'll either be given the entire formula sheet or this little piece of it in order to use as a reference. And that is it for today.